For this April edition, it's a pleasure to have Michel Brion for this seminar, who will give a talk about projective homogeneous varieties over a field.
Okay, thank you for this invitation and opportunity to speak. And sorry for the delay. As you see, my familiarity with Zoom is extremely rusty. And actually, every time I can, I avoid using this, but I'll make an exception. So I will talk about projective homogeneous varieties and start over the field of complex numbers, where these varieties are mostly well known, then discuss them over a field of positive characteristic, algebraically closed, where actually there are many more, and they have been understood very recently. And then over a field, which is the topic of the talk, and then what I will say is joint work with Mathilde Maccan and Srimati Srinivasan, which is in progress. So I won't claim we understand everything, and I will just report on some parts we believe we understand, okay? And I also I think that maybe most of you are more familiar with algebraic geometry over the complex numbers, and here this will be over a field. So please feel free to slow down and ask questions if things go a bit too fast or too obscure. Okay, so let me start with, well, can one see this? Okay, maybe better. This homogeneous varieties over a field, which is algebraically closed. So the definition of these varieties is just varieties with a transitive action of the automorphism group. Since I'm working later with an arbitrary field, I will be fussy and distinguish between a variety and its points over the ground field, even if for algebraically closed fields, not a big issue. And then the main theorem says that every projective homogeneous variety is decomposed as a product of an abelian variety and a rational projective homogeneous variety, okay? And this abelian variety is just an algebraic group, which is, say, projective and connected. And Y is, well, what all these names say, rational, projective, and homogeneous. So this was proved by Borel and Remmert in 1962 over the field of complex numbers, actually for compact Kähler manifolds. So the result is even more general. And in the above formulation, what you need to do is replace A, an abelian variety, with a complex torus. And this Y part doesn't change. Then it was also known at the time that this Y part is just some G mod P, homogeneous space under a complex semi-simple algebraic group, where P is a parabolic subgroup. And these objects were well known at that time, and I will briefly recall how they are classified. And much later, actually 40 years later, this was extended by Sancho de Salas to positive characteristic, still algebraically closed field. Then the statement is the same, but in this G mod P, you can allow non-smooth parabolic subgroup. I will give examples of these strange objects soon. At that time of Sancho de Salas, there was a classification of these objects for characteristic bigger than 5. So the cases of characteristic 2 and 3 were missing, and these were handled by Mathilde Maccan during the last 2 years. That was her PhD. I will not really explain the results of Maccan, which are very nice, but a bit involved. I will present those of Wenzel, which are easier to state and necessary for the talk in a couple of slides. In the next slides, I will go through some example in positive characteristic when you see this non-smooth business. And it starts with a hypersurface in P2 times P2, projective space times itself, with a homogeneous equation of this form, some powers of the first variables, this x1, x2, x3, are the homogeneous coordinate on the left P2. And of course, this y1, y2, y3 are those on the right P2. And you put some powers of P in the first variables. These powers of P might be 1, and what you get in the, 0. What you get is x1, y1 plus x2, y2 plus x3, y3 equals 0. And this is the so-called incidence variety geometrically. You think of this P2 as a P2 of points, the other P2 as P2 of lines, and the equation tells you that the line goes through the point. And this incidence variety is also the flag variety of the group SL3. This is SL3 mod B, where B is a kind of standard Borel subgroup. In this geometric situation, it's a stabilizer of the first coordinate point, 1, 0, 0, and the last coordinate line, x3 equals 0. And this is also the upper triangular matrices. And the action of this x on these coordinates is the natural action on the first coordinates and the dual action on the last ones. Then for an arbitrary number m, you can twist this action to make this equation invariant under SL3. So you still act on the first variables in the obvious way by linear change. And on the last variables, this y1, y2, y3, you act by the pmth powers of the matrix to get the correct power, and then inverse transpose to get the invariance of the equation. And it's easy to see that this variety here, xm, is still homogeneous. And so it's G mod P, where P is a stabilizer of this pair, which is still there. So let me describe this P for you in the next slide. If you write in matrices, formally, you obtain that these matrix coefficients are 0, and this one is 0 after pmth power. And you see it's a non-smooth variety because non-smooth scheme because you have a non-reduced part of this equation. And if you take the associated reduced scheme, you take the solutions of these equations, you find back the Borel subgroup where all these matrix coefficients are 0. Well, you certainly know that this Borel subgroup is P1 intersected with P2, where this P1 and P2 are the maximal parabolics, which fix the standard point on the standard line. And now for this group P, what you get is P1 corresponding to these two matrix coefficients being 0. And then intersection of a flattened version of P2, where you multiply this P2 by a so-called Frobenius kernel. Frobenius kernel is the kernel of the endomorphism of G, which sends a matrix to the matrix of P to the mth power. If you write this and do a little bit manipulations, you get that this equality is equivalent to this one. Okay, so I write this on this form because that's how this was generalized by Wenzel to all non-smooth parabolics. Let me state this in the next slide. Now I'm working over an algebraically closed field of arbitrary characteristic. I take a semi-simple group over this field and a Borel subgroup. And then it's known that this Borel subgroup is contained, actually the intersection of finitely many maximal smooth parabolics. So I add the word smooth everywhere to the objects you're certainly familiar with. So these maximum ones are in number R, which is a rank of G. And every smooth parabolic is a partial intersection of these ones in a way which is unique up to reordering. Probably you're also familiar with the presentation of this using root systems. Well, I will not use it in the talk, even if it's natural and everywhere in the arguments. I will just stick to a geometric formulation. Because out of this, you can go to the non-smooth parabolic subgroups in characteristic bigger than 5. I will explain this a bit later. Then the statement is that every parabolic subgroup is conjugate in G or G of K to a unique subgroup which contains B. And this unique subgroup is an intersection of PIs fattened by Frobenius kernels. These are these gadgets here and here, and in the middle. And so the data, which are these pairs MI and MJ and IJ, are unique up to reordering. So why does it hold in characteristic bigger than 5? Because, well, the moral reason is in small characteristics, you have new phenomena arising from vanishing of structure constants in the Lie algebra. You probably know that the Lie algebra of G can be defined over the integers, and the brackets, structure constants, are integers between 0 and 3. So in small characteristics, some of them disappear, and this creates a possibility for new Lie subalgebra, and hence for new, morally, ways to fatten these parabolic subgroups. And this is indeed the case, and was discovered by Mathilde Maccan. Again, I will not give too many details on this. Maybe it will deserve some separate talk because it's a long story, which interesting twists. So I will mostly work in characteristic P bigger than 5 in the sequel. Then I will move to an arbitrary field of any characteristic and fix an algebraic closure. And first of all, we need a notion of homogeneous variety in this setting. So I will say that a variety with an action of a smooth algebraic group is homogeneous if over the algebraic closure you get what you expect. That the k-bar points of the group acts transitively on the k-bar points of the variety. Well, this doesn't mean that X has a k-point, and we will see examples where this doesn't happen. But over the algebraic closure, we have a nice and standard way to think of this variety. This is a homogeneous space, G bar. G bar is this G over the algebraic closure, modulo the stabilizer of any k-bar point. This stabilizer has to be understood as a subscheme, and as you see, it's not necessarily smooth. So from this fact, you get that homogeneous varieties are smooth and quasi-projective because this holds over the algebraic closure and this descends. But again, they might have no rational point. The standard example is quadrics. Well, you take a non-degenerate, quadratic form in n variables, where n is bigger than 3, and you consider the associated projective quadric, the zeros of this quadratic form in the projective space. And of course, it's a projective variety, and it's homogeneous under the special orthogonal group of this form, which is semi-simple by this assumption n bigger than 3. And over the algebraic closure, you get this structure. But as you know, quadrics may have no k point, and the standard example is take for k the field of real numbers, and for q the sum of squares of the coordinates. Then you see you have no r point of your quadric, and this group SOQ, which is now SONR, has no parabolic subgroups at all, except the full group. Well, there is no Borel, no parabolics, so you have to live with this. Then I will also give an example from geometry, just from algebraic geometry, which is kind of opposite to the earlier example, which is purely algebraic. I will consider a family of smooth projective curves of genus G over some base S, which I will assume to be a variety. So what do I mean? This F is a smooth projective morphism, and the geometric fibers are curves of genus G. And then I'll consider the generic fiber in the sense of algebraic geometry. This S, which is a variety, has a unique generic point with residue field, the function field of this S, and the fiber at this point is a curve over this function field. In genus 0, what you get is a so-called smooth conic bundle. Maybe the fibers are not projective lines, but at least they are conics in a canonical way. And in particular, the generic fiber is a conic and is homogeneous under SOQ, where Q is a non-degenerate quadratic form in 3 variables over this big field K. And if G equals 1, then what you get is curves of genus 1, which are almost elliptic curves. But you should remember that in an elliptic curve, you have an origin, some fixed k-rational point, and here there is none. But you can more or less reduce to the case of elliptic curves by considering the so-called Abel-Jacobi map, which sends your family to the Picard scheme of degree 1, just sending the point to the associated invertible sheaf. And it's easy to see this is an isomorphism. And in particular, if you apply to the generic fiber, you find that X, this fiber, is isomorphic to peak 1 of X. And peak 1 is a homogeneous space under peak 0, the divisors of degree 0, which acts just by translation. And now in this peak 0, we have an origin, which is a trivial bundle. It's still of genus 1, so this is an elliptic curve. And this action by translation is has a trivial stabilizer, so what you get is a G torsor, or otherwise say the principal homogeneous space under these elliptic curves. But in both cases, there are many examples where you have no k-rational point. This means geometrically that the family has no rational section. And you saw this for quadratic forms, for sum of squares, for the real numbers, and for curves of genus 1, this exists over the field of rational numbers, for example. And what I should also mention is if you work in positive characteristics, then this function field K is usually imperfect. unless it's a small field you started with. So we definitely have to consider imperfect fields in this business if we want to deal with these objects. So now I will generalize the Borel-Remmert theorem to this setting. So I'll start with a smooth algebraic group and a homogeneous variety under this group. While there are a couple of reductions, we may assume that this group is smooth and, well, sorry, connected and act faithfully, otherwise we divide by the kernel. And then we get generalization of this Borel-Remmert theorem, but one has to be a bit careful and decompose X and the acting group simultaneously. This is actually a good thing to do in this setting. So what I claim is, under this assumption, G is a product of an abelian variety by a semi-simple group, which is adjoint because it acts faithfully. This is as in the Borel-Remmert theorem, and X is a product of two terms. The first term is a torsor over this A, and the second term is a homogeneous variety under this H, which is projective. This is not far from the results of Borel-Remmert and Sancho de Salas, because once you get a statement which makes sense over every field, you just prove it by some small arguments. And I will not give these arguments, these are not deep. But the moral of this is one can concentrate on the case where the group is adjoint semi-simple and well, the variety is what it is. And that's what we will do next. So I will consider a semi-simple group and X, which is projective homogeneous under this group. So over the algebraic closure, we get we are supposed to know quotient of the group by a parabolic subgroup. Well, there is a useful fact that in this situation, this H is this known normalizer, also as a group scheme. And so this homogeneous space is a parameter space for conjugates of H. So it could be called a parabolic variety, and that's how it is called in the literature. So we are not sure of the right terminology. In this talk, I will use generalized flag variety under the additional assumption that X has a k-rational point, which, as you saw, is really an additional assumption. And then comes the first observation. If the field is perfect, then the k-points form a unique orbit of the group of k-points. And the proof is easy if you quote the right paper. So let me give it. So if you have a smooth parabolic P, which is a stabilizer of this point, then this is known by the work of Borel and Tits. And the reason is that, of course, X is G mod P, and the map from G to G mod P is a locally trivial P torsor for the Zariski topology. So it has local sections, and you can always lift k-rational points. And for a non-smooth P, this is wrong, but we can use a reduced subscheme, which is a smooth subgroup, and we can use the natural map from the G mod P red to G mod P. And by general nonsense, this map is finite and purely inseparable. And now it's a nice exercise to show that every such map induces a bijection on k-rational points. And then you just conclude by this Borel-Tits result. So next, we will see if you work over an arbitrary field, this proposition gets wrong. But still, there is a nice orbit of G of k that we will use. And that's what I want to do next. So that's what I was trying to say. Over an imperfect field, if you go back to this hypersurface Xm in P2 times P2, one can check that it has infinitely many orbits of the group SL3K. And then you can take any imperfect field, even one with finitely many extensions in any given degree. So it's a kind of non-intuitive statement. But there is a nicer orbit of k-rational points that I will try to introduce. This is based on a very important result of Borel-Tits, which says that every semi-simple group over a field admits minimal smooth parabolics. Well, this is obvious, but the theorem is they are all conjugate under the k points. And in the theory of Borel-Tits, these minimal parabolic subgroups are a substitute for the non-existing Borel subgroups. And you will see this is really the philosophy we follow in this talk, in our work, as a kind of guiding principle. So the first thing is a kind of substitute of Borel's 6-point theorem, which says if you have a generalized flag variety under G, this is again a projective homogeneous variety with having a k point. If P bigger than 3, then it has a unique k point, which is fixed by this P min. So P bigger than 3 is for some rather complicated reason, and we hope that it's not needed, but we cannot prove it. Okay. Well, maybe I'll discuss this at the end if I have time. So starting with this, we can really get many interesting informations on our variety X. So let me list some of them. So this is a reminder of what happened. So these are the assumptions. We have a kind of base point, small x, its orbit, which consists of the points whose stabilizer contains a smooth parabolic subgroup. So we have the stabilizer of this point, we have its largest smooth subgroup, which is, of course, a smooth parabolic. We take an opposite one in the usual sense for people used to this. Then we get a kind of open cell in the group G, which is a product of the unipotent radical of Q minus by Q. Product in the sense, image of the multiplication map. And then the claim is, if you restrict this decomposition to the subgroup P, we get an isomorphism of schemes. Here comes P, you get this Q, and then you get some intersection of P with a unipotent radical. Sorry, there is a minus here, which is missing. I will go back to this in the notes, right? But this is definitely minus. And the statement is, this subgroup is so-called infinitesimal. It has a unique point, which is its neutral element. Actually, one can really describe its structure in a very precise terms, and that's what Wenzel did and what we generalized. Well, maybe this is a technical development that I will skip, but you see that this subgroup P is just the usual parabolic subgroup Q fattened by this infinitesimal subgroup. So next, I will explain that this variety X is rational in a very strong sense, because if you take this orbit of the base point by the unipotent radical of opposite subgroup, the claim is it's open in X and isomorphic to an affine space. And also X is covered by the translates of this orbit by k rational points. And this means, as I mentioned, that this variety X is rational in a very strong sense. Every point has a neighborhood which is an affine space. Well, let me explain briefly why this holds. First of all, that the orbit is open is not a big deal because you have this decomposition. If you apply it to X, you get this openness. Apply this to the base point. Being isomorphic to an affine space, this is because this is an orbit of a unipotent radical here. And this unipotent radical is not an arbitrary smooth connected unipotent group, it's split. It's an iterated extension of additive groups. And then it's a known result, not a trivial one, that every homogeneous space under such groups is an affine space. So finally, I will explain how Wenzel's classification of parabolic subgroups extends to an arbitrary field. So let me maybe get back to this classification. That was here. This was over an algebraically closed field of characteristic P bigger than 5. And you saw that every parabolic subgroup is an intersection of maximal ones containing a given Borel, fattened by Frobenius kernels. And now then let me get back to this business. So here we use another result of Borel and Tits. By the way, this paper of Borel and Tits is called Group Reductive. It goes back to 1965. And it's a fantastic paper because they do what the structure, what the title suggests, describe the structure of reductive groups of an arbitrary field, and they do this completely. And again, their main idea is to replace Borels by minimal parabolics, and also to replace maximal tori by maximal split tori. And this is apparent in this statement that this group G has finitely many maximal smooth parabolics containing this fixed one P min. And the number of these parabolics is a split rank, which is a maximal dimension of a split torus. And the smooth parabolic subgroups, as you expect, are partial intersections for those which contain P min. And, the final statement of the talk is if you remove smooth, then you get the following version of Wenzel's result. You just add Frobenius kernels in front of each maximal parabolic factor. So you get this, which is a kind of full structure theorem. I will briefly explain how to prove this. Of course, we just try to deduce it from Wenzel's classification, which is over the algebraic closure. But this doesn't work because to work, for this kind of argument to work, we need some kind of Galois descent. And Galois descent from the algebraic closure is impossible task if the field is imperfect, only works over perfect fields. So what we have to do first is to extend Wenzel classification from algebraically closed field to separably closed fields. Okay, this is a technical issue. And I won't say it's completely easy, but the good news is the structure of semi-simple groups is the same in both cases. It's also something Borel and Tits taught us, that semi-simple groups get split over a separable closure of the field. So they get as usual. And then we can use Galois descent from the separable closure. So the ingredients as follows. We choose our minimal parabolic, maximal split torus there. these pairs S and P mean are all conjugate under G of K, so this choice is not too serious. Then we choose a maximal torus of P mean containing S. Then there may be several kinds of them. But then we go to the algebraic closure or separable closure, and we get this inclusion. So I'm very sorry because in this slide, this bar denotes going to the separable closure, which is a case I just alluded to, not algebraic. Then we can use classification over the separable closure. We get some intersection of maximal parabolic subgroups fattened by Frobenius kernels. And now the Galois group of field permutes these terms because everything is, every ingredient is defined over this the ground field and stabilize this one. So we can group these terms together according to their orbit of the Galois group. And this is supposed to give you back these terms here. So of course, I'm cheating at this point, but I think it's really a matter of technique to get this get a full proof. So at this point, I will stop the formal part of the proof. I will just give you a small list of references. So this is the original paper of Borel-Remmert. This is a paper of Borel-Titz. Then, as you see, there are some really recent work of Mathilde Maccan and Ronan Terpereau on projective homogeneous varieties in small characteristics. These are these two ones. And well, these horospherical subgroups are generalizations somehow of parabolic subgroups. They are studied in positive characteristics in this paper. Characteristic bigger than 3, if I'm correct. And then comes this paper of Sancho de Salas over an algebraically closed field and Wenzel. And I think that's all for the formal part of the talk. So now please feel free to ask questions or make comments or whatever. Oh, I realized I was very quick. So if you want me to get back to some part of the talk, please feel free to do this.
Okay, thank you. Thank you very much for your talk. Are there questions? Yes. So Gregor Kemper, please go ahead.
Well, I'm clapping, I'm applauding to the talk. Thank you very much, Michel.
Well, thank you for listening. That's the first talk we give on this topic, so you see some way to, okay, to improve, but you have to start.
So are there questions?
Yes, I am Nina.
Yes.
Sorry, I am very new to this topic, but just wondering is how is this algebraic groups different in positive characteristic? There's in the beginning you said that in it may not be smooth certain things which.
Well, probably I should have been slower on this because well, maybe I'll get back to some parts of my talk. Wow. Okay. Sorry. So let me say it in words. In positive characteristics, some algebraic groups are not smooth, and some of them are even some kind of fat points. So
Mhm.
they have only one point over any field, which is their origin or neutral element, but they are non-trivial finite groups. And the basic examples are groups of p-fruits of unity. Okay, so
Mhm.
well, over any field, there is a unique p-fruit of unity in characteristic P, which is one. But there are plenty of p-fruits of unity over rings, which have nilpotents. Just take one plus something of square zero. So what you get in this way is a group scheme, which is of order P, and which is not smooth at all. And
Yes.
yes,
Yes. 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 So in
and
this way, we could say it,
and
it,
that,
it can then it's done different from characteristics,
yes, and you have the same phenomenon with matrices. If you think of the general linear group, all
Yes.
invertible n by n matrices, you can take matrices such that if you raise all the coefficient to P, you get the identity matrix,
Mhm.
right?
Yes.
Okay, this is
Yes.
a good. It's highly non-reduced, and over any field, its unique point is just the identity matrix.
Yes.
But for the above reasons, it has plenty of points over rings with nilpotents. So that's a basic example of Frobenius kernel. And you can
Mhm.
put these Frobenius kernels everywhere in your business and spoil the picture you had in characteristic zero, or make it more interesting.
What would be a good place to start with or see a good survey of these things?
Sorry, I must say I didn't understand the question. Can you please repeat?
What would be a good place to start for a survey to these results?
Well, there's a survey. There's a book by Milne on algebraic groups, which is
Yes, yes.
really written from the viewpoint of group schemes.
Mm-hmm.
Well, it's a great book to look for results and motivations. I must say it's not a great book to look for correct proofs, but maybe that's irrelevant. If you want to get an idea of the theory, nice examples and nice statements, maybe you can start with this book of Milne. Title is just algebraic groups. Okay, so easy to
That's
remember.
nice. Good reference. Yes. Thank
Okay.
you. Thank
Otherwise, I
you very much.
survey for on finite group schemes, which is really
Mm-hmm.
extremely basic. So it's a pre-graduate school survey. You can have a look just to look at examples of an algebraically closed field and without any
Mm-hmm.
big theory. The title is finite group scheme, so it's an easy thing.
Okay. Thank you.
Further questions? Okay, since there are no further questions, so let me ask you some rather basic question.
Mhm.
It's something what you said during the talk. So you had some group, for example, SON
Yes,
over a non-closed field,
yes,
and so you said that there are no Borel subgroups, and
yes.
as far as I understood. So, but as far, I mean, I don't really understand it. So you mean non all Borel subgroups are conjugate, or you mean that there are no Borel subgroups? So
Well, what I mean exactly is, first of all, there are no parabolic subgroups,
okay,
meaning if you take any subgroups P of G, such that G mod P is projective, then P is a whole G. And then there are no, of course, you can think of maximal solvable connected subgroups,
yes,
call them B, but then G mod B is not complete or projective.
Okay.
I should not call them Borel subgroups. So that's
Okay.
maybe there are none. I mean, you always have maximal tori in these groups,
Yes.
and sometimes you cannot go beyond maximal tori. For example, in SONR, you have maximal tori, which was SO2R times SO2R, as many as you can fit. But then these are maximal connected
This is a
subgroups.
maximal solvable, you mean?
Even maximal connected subgroups.
Ah,
I think.
Maybe you
Okay.
can take the non-trivial real form of SL2, call
Yes.
it SU2, where there is a non-split torus inside, and that's
Okay.
the maximal connected solvable subgroup.
Yes.
And do you know something like how many there are of these Borel subgroups? I mean, Borel maximal solvable connected in for example in SON or something. So are there infinitely many? Is there some work about classification of these Borel subgroups? Or
I must say, I don't know. It's a very natural question. I don't know because I'm immediately thinking of those which contain maximal torus. Maybe you can have some other ones. And anyway, you have several kinds of maximal tori. These maximal tori are no longer conjugate.
Exactly. So it can be
So
split and split or something.
yes, that's a first difficulty, right? If you think of quadratic forms, you can think of tori with the split part corresponding to the form having factors like x squared minus y squared. Okay, creates some G, and x squared plus gm plus y squared. Sorry, creates some SO2. And as you know, real they are different. And well, so you can imagine plenty of different maximal tori to start with. There is a theorem saying there are only finitely many conjugacy classes of such tori over the real numbers.
Okay. I see.
Not over an arbitrary field. So you see, things are really very different. No,
Okay.
you for your question.
Okay. Good. Thank you. So, any further questions? Okay, if not, then let's thank Michel again.
Well, thank you for coming for this Easter seminar.
Thank you.